Right, so good afternoon or good morning. This lesson is about the search algorithms that we had discussed in our lecture. So we are going to apply our learnings in the laboratory session. So for this lab exercise, we will be having, or we are going to use Google Colab, or you can also use Jupyter as your notebooks in processing this laboratory exercise. So the tools under Python, we need to have the libraries Matplotlib, NumPy, NetworkX, HeapQ, and collections. So for this lab exercise, you will be able to implement the searching algorithms, both informed and uninformed, compare algorithms by path, cost, and nodes expanded, and apply search to a roadmap and maze. No? So what is expected to you guys is the first thing that you're going to do rather is for you to set up the required libraries for us to be able to run the entire program. So for part one, you are expected to create a graph. So I want you to copy the initialization of the graph. So what this means is that from point A to point B, you have a path cost of 2, then A to C is 5. So the start node here is the A, and the goal node here is F. Now, how do we visualize it? So in visualization, we need to call the graph function and then use looping statements for us to graph all of the edges and its weights. So if we try to run that, we have this graph here from A to C, 5. So it's mentioned here. A to B is 2. Then and so on and so forth. So we can also see that here reflected in our visualization. Applying BFS for us to go to the path from A to F, no? So we have to use the Q and then print the path, which is ACF. Okay, so just copy that. Similarly, using DFS, use the code, no, stack, and then start, and then print the DFS from path A to F. So which is using the DFS, no? If you could remember in our lesson, the depth first search searches from each of the depth of or level of depth of the tree. Using uniform cost search, so we use this code here, and then if we print that, we can get the shortest minimum cost of 8 of the path ACF, and the greedy using inform search naman. So this is our heuristic tentative, no? So you have A as 6, B as 4, C 2. Mm, if we print the greedy path, we still have ACF, and this is the code for that one. And using A star search, the cost is also 8, but it is already informed, no? Meaning we have already added the heuristic and the path cost for both. So that is the application for the searching algorithms that we have in searching algorithms. Now, we do apply it in real world scenarios such as the roadmap searching. So for example, we have the path cost from Davao to Tagum as 55, Davao to Jensen as 150, and then we want to visualize it using the same code earlier. We can apply this in roadmap searching, right? So we also define the heuristics to Butuan from Davao, that's 320, Tagum 230. Of course, this is 0 since it is the destination. Cagayan de Oro is 130. Then Jensen is 400. So using UCS or the uniform cost search of the roads from Davao to Butuan, we print that together with the greedy and the A star algorithm, we can have, or we have this visualization, or we have this output rather, as so UCS, since it prints the path cost, it gets that it's 285. The path cost is 285, and the path is from Davao Tagum to Butuan, right? So they have the same output, greedy, using the greedy search algorithm as well. You have Davao to Butuan as Davao Tagum Butuan as the path, right? So it goes from Davao to Tagum to Butuan, and also the A star, so using that path Davao Tagum to Butuan as the shortest path and has the lowest path cost. So if we have complicated trees right there using this code, and if you want to add more nodes or more destinations, you can use this code. And applying it to the maze navigation, what happens here is that this is, for example, in our Cartesian plane. No, looking at this maze right here, remember that zero there is a path that we can go. No, pwede nato siya agihan. So if we have 0, 0, 0, 1, 0, that is our first array, or first set of location in our Cartesian plane. So starting from that, the next is we have 0, 1, 0, 1, 0, right? Going back, that is right. And then 0, 1, 0, 0, 0, 1, 0, 0, 0. So given this maze right here, our goal is from 0, 0, which is on this case here. And then we want to like search the maze, what is the shortest path or the path cost, or which is the shortest path. I mean, using the different search algorithms, no? Kasi si greedy algorithm uses or is under the Dijkstra's, that's just the shortest path. So we will use the different path search algorithms, no, to go from this point, from 0, 0 to 4, 4. So that's the start to the goal. And we define the neighbors, no, using the functions, Manhattan, BFS grid, the A star grid. And using these BFS and the A star path, we visualize, no? But before that, we print first the path, no, and the grid cost, and the A star grid path and the A star grid cost. So we have here, the path is from 0, 0 to 1, 0 to 2, 0, 3, 0. That is using the breadth first search. But for the A star grid path, it's 0, 0, no? Tapos, ato siya sa 1, 0, then 2, 0. Then, similar, path cost, which is also 8, because each move here, that's one path. 1, 2, 3, 4, 5, 6, 7, 8, to be able to arrive at the destination. So you see, different search algorithms, they reach to the same goal. However, they have different algorithm. So this is uninformed search algorithm, and this is informed search algorithm. And then afterwards, you're going to answer or fill in the table using the outputs that you have here. So you have to write the path cost, if it's optimal or not. Okay. And then answer the reflection questions. Which algorithm guarantees the shortest steps and the lowest cost? How does heuristic admissibility affect A star's optimality? And in your field, where would you use both BFS or DFS and UCS or A star apply in your field? So I'd like you to open your lab exercise and start working on your own about the search algorithms. And I hope that you will learn something from this laboratory exercise. Thank you so much for listening. See you on the next one.